I'm QP. I'm here to present you this talk, teaching an ODAG new tricks. So in this talk, I'm going to talk about how Scribd deployed Airflow into AWS Cloud with best practices and some of the learnings that we had along the way, as well as some of the issues that we ran into and how we solved them. So this talk is broken up into mostly two parts. The first part, I will talk about cloud native deployment of Airflow into AWS. The second part, I'll briefly go through how we migrate from our internal batch orchestration system into Airflow, and how we migrate from a physical data center into the cloud. How we plan, execute in multiple steps with incremental deliverables to external teams. So for those who are not familiar with Scribd, we are a subscription service for reading. So with $9 a month, you can get unlimited access to books from major publishers, audiobooks, magazines, news articles, and all the goodies. So you can sort of think of us like Netflix for reading. And about a year ago, we published this blog post on our company tech blog about announcing that Scribd is moving to the cloud. Due to our ever-growing customer base and the engineering team size, it's clear to us that we have to move to the cloud in order to move fast. And this gave us a golden opportunity to step back and really rethink how should, if we're going to redesign the infrastructure from the ground up in the cloud, how would we design that using all the best toolings that's available today? So when we design this Airflow deployment, we have a couple guiding principles in mind. The first one is to use managed service whenever possible. When I say that, I mean when we need a MySQL database, we will make sure that we use RDS, right? We don't want to manage MySQL ourselves. We use EKS to manage the Kubernetes cluster instead of standing up our own. So some people might ask, why don't you just use the managed Airflow? In fact, companies like Astronomer, they actually provide really good managed Airflow service. If I am to start a new data pipeline from scratch today, or if I'm starting a new company, that's definitely the first thing that I'll consider. Scribd, it's in a little bit special case because we have a really old and quite complex internal data pipeline that we have to migrate to Airflow. And when we were evaluating the old system, we noticed that a lot of the features doesn't even exist in Airflow. So we have to do a lot of customizations, right? So we weren't really sure that whether all those customizations will work well with a managed solution that like the ones that provided by Astronomer. But I do think if for any like greenfield project, it's better to just use a managed SaaS product. That would definitely save you a lot of work. By the way, disclaimer, I'm not paid by Astronomer to say any of this. This is just my personal belief. I think in general, nowadays, developer times, engineering times are much more expensive than whatever cloud SaaS product that you will be paying for. The second principle is separating of stateless compute from stateful data store. So this basically guides us that during the design, we want to push all the components into the stateless part as much as possible and keep the stateful part minimal, right? So the reason for that is to make the system a lot easier to operate. For the stateless part, you can just kill it, you can destroy it, recreate it, and it won't have any major impact to the system. The third principle is for separating of infrastructure and application. So here, infrastructure, I mean, what I really meant is Airflow cluster, right? So the actual Airflow code. And then by application, I mean that the DAG that's developed by the external teams. The reason we have this design principle is so that the application deployment can have its own deployment cycle, and that's not tied to the Airflow deployment itself. so that the external teams can iterate on a much faster pace. And also, the application code will not have any impact to the infrastructure itself as well. And then the fourth one is separation of environments. This is a really common practice. You want to have a that development, staging, and production environment for all the services. And lastly, we want to automate everything. We want to automate as much as possible with code. But so in this specific case, we're using Terraform to basically provision all the cloud resources we need, and this in turn helps us to provision the Airflow cluster in different environments very easily. And then the last one is not really a guiding principle, but it's a fact that we run the latest development branch of Airflow in production. This is not something that I would recommend most people to do unless you really understand the internals of Airflow and you can fix any bugs without depending on upstream maintainers. But like I said, with great responsibility, comes with great power, right? So running this on running the latest development branch in production also gives us access to all the latest features in Airflow, all the latest bug fixes, of course, also all the latest bugs. But overall, I think it has worked out really great for us. There were a couple times where the DB migration will fail. I will go into manually run queries to fix the DB migration script. But what the biggest benefit we get from this is it makes it a lot easier for us to keep in sync with the upstream code base because we have a lot of internal customizations. It makes it easy for us to send patches upstream. So when we started this project, we have an internal fork of Airflow. Today, we're actually running just the upstream Airflow in production because we have already sent all the internal patches upstream, and the merge was really easy because we actually run on the master branch. So this is a quick overview of what it looks like in AWS. So there are a lot of services and diagrams. Don't be overwhelmed by this. I will go into details in some of those icons. But the main thing that you want to focus on is the Airflow components. So we have the Airflow web and Airflow scheduler, right? Those are actually running in the ECS Fargate. And then we have the Kubernetes executors that runs in EKS. We use RDS for the MySQL. We use ECR to host the Airflow container image. And we use S3 to host the logs and as well as the DAGs. So first question people might ask for this is, why the hell are you using both ECS and EKS? They both serve the same purpose, right? They are a platform that you can use to deploy containers into the cloud. That's actually a really good question. The reason we split this up is it sort of goes back to my earlier slides where we have this principle of separating infrastructure from application, right? So for the infrastructure part of the system, like the Airflow scheduler, Airflow web, we actually deploy that into ECS Fargate. And for the application, it goes to EKS so that we can literally, if anything goes wrong with the EKS cluster, we can literally just purge the whole cluster, right? We can recreate it and things will still go fine. If anything goes wrong with the ECS cluster, we can again delete the whole cluster we created. It won't affect the task that's running in EKS. And the other reason is we actually had pretty extensive experience with both EKS and ECS in the past. One thing that I personally noticed is although ECS is a lot less flexible and a lot less powerful compared to Kubernetes, it's actually a lot more stable, right? So especially in AWS. So we have never had any major issue with ECS in the past, but we have had a couple pretty big outage with EKS. So by moving the infrastructure into ECS, it will make the whole system a little bit more stable. And because of the ECS Fargate, we don't even have to manage any machine ourselves. It's sort of like a serverless container platform, so that we only have to ship containers, right, without managing anything ourselves. So this also reduced the operational burden on the team. It wasn't really a smooth sailing at the beginning. So when I first set this up, I was really happy for about 40 minutes. Everything went fine until the scheduler all of a sudden started to crash with errors, exceptions pointing that API token is not valid anymore. So what we did a deep dive into that. What actually turned out, what actually happened was for authentication with EKS APIs, we actually use AWS IAM Authenticator. Um, this is the binary provided by AWS that's responsible for fetching a API token based on the current IAM role. So this token turns out that expires roughly every 40 minutes. So if you try to communicate with the EKS cluster, that's in Airflow terminology, we call this out of cluster mode, where the executor cluster actually doesn't run within the same Kubernetes clusters that the Airflow itself scheduler is running. So when you have this combination, your scheduler will only work for the first 40 minutes. So we got this bug fixed. It was not an easy fix. It actually the fix spans multiple open source projects owned by different organizations. So we noticed that it might take a long time for the Kubernetes team to release a stable client with this fix. So we also backported this fix into Airflow. So if you're using Airflow today, communication with DKs should work out of the box without any issue, hopefully. Another special setup that we have is enable teams to develop their own pipeline and own DAGs within their own Git repo, right? So they can have as many Git repo as they want. DAGs will get pushed into from CI/CD into a shared bucket using a command line that we provided. And those DAGs will be synchronized from S3 into different Airflow components. So if you have been watching all the previous summit talks, you probably have noticed that this is something that a lot of companies are doing today. So I think that's a good direction to go. And we actually wrote about this setup in details in the engineering blog post that I linked at the bottom of this slide. So if you are interested in replicating the same setup, there are step-to-step guides in the blog post. But I do want to share a little bit details on this setup specifically because this part we actually did it a little bit different compared to other companies that I've seen so far. So we actually built a DAG sync daemon in Golang, right? So the goal of this is to make sure that the CPU usage and memory usage is as low as possible, because this is a daemon that will be running alongside the actual Airflow components. So we want to have a minimal impact to the actual Airflow code. It's a single binary, so it's really easy to deploy this. It keeps the list of the DAG files and checksums in memory, so to minimize network and disk I/O. So basically, if there's no change in the DAG repo, you should see almost zero I/O from this daemon. And because of this, we can run this sync process in a really tight loop. And from our experience, at the time from a DAG get released from a CI/CD pipeline, from it getting picked up by different Airflow components, or usually takes only within seconds. So it's a really quick release process. We do have some future plans to even further optimize this. We're thinking of using the S3 event notification feature to basically turn this into a push event system. So any DAG change in the S3 bucket will get pushed into DAGsync daemon, and they will be able to fetch the latest updates in near real time. And another benefit of running a daemon is you can actually expose HTTP endpoint and then expose some of the metrics in the Prometheus format. So in this daemon, we actually expose the statistics for the DAG files. the time spent on DAG sync, and the daemon uptime. So all of this is important for us to monitor and make sure that the DAG sync is working as expected across many machines and nodes. And this project is also open sourced, so you feel free to take a look and see if it fits your need. Another interesting thing that we did with Airflow is to manage all the variables with Terraform. So so for those who are not familiar with what Terraform is, it's a tool to basically provision any kind of resources that's backed by API with a declarative syntax, right? So a common usage of Terraform is to use it to provision AWS resources. In this case, because Airflow itself also has REST APIs, we can actually use Terraform to provision resources within Airflow itself as well. So a variable is a really good example in this case. So we leverage a variable as Scribd for a lot of different things, but it gets a little bit messy very quickly. So this is an example of what a variable look like. This is a single variable in Airflow, right? So if you look at this, it's really clear that this is not readable for a human. There are a lot of numbers in it. I have no idea what those numbers are. They actually, most of those are AWS accounts, but I don't know if those are from production accounts or development accounts or staging accounts. It's just really easy to make mistakes. And it drives me nuts that I have to manually maintain all this every time someone sends me an update request. So what I ended up doing is building a Terraform provider for Airflow. So in this case, this provider exports a Airflow variable resource that you can use to define a variable in an Airflow cluster. And we also, combined with this provider, we leverage the Terraform remote state feature. So what the remote state is, basically for each Terraform stack, you can choose to export some of the variables into the output, right, which can be consumed by other Terraform stack. So in this output, you can actually put the AWS resource arms, different kinds of account IDs or all sort of stuff. And then the other Terraform stack can reference those values using a variable name. So in this case, we have team A output its Terraform state as output, and then within this Terraform file, we can just reference those AWS arms using variable names. So now everything is readable by a human, so it's a lot less likely to make mistakes. So the current Airflow, the Terraform provider, only dumps all the variable files into a JSON files, and we use that to manually import everything into Airflow. But this is starting to change, because if you have watched the Future of Airflow keynote, you might have noticed that Airflow is going to have a new set of REST API that's backed by OpenAPI spec. So what I've been working on is to working with the community to generate the first Airflow client using the API spec. The first client will be in Go, because I'm going to use this for this provider, right? So I already have a working demo locally where the provider can use the generated Airflow Go client to actually interact with Airflow APIs, the new REST APIs, and manage the variables within Airflow. So once we have authentication added to the new REST APIs, I will be able to deploy this new provider into production as Scribd. The next thing that we do is monitor Airflow end-to-end with Datadog. Datadog is the monitoring solution that we use as Scribd. It's actually really straightforward, because Airflow has its own statsd integration. So we just basically deploy the Datadog agent as a sidecar container in ECS on the left, and then on the right, we configure the scheduler to send all the statsd metrics into the agent, which gets pushed to Datadog. But having just the Airflow internal metrics, it's not enough, right? So we also need metrics for the infrastructure layer. So the core platform team and core infrastructure team at Scribd, we actually collaborate to build a Terraform AWS Datadog module. So with this module, you can actually synchronize all the CloudWatch metrics into Datadog with a couple lines of code, and now you can put all the important metrics for Airflow into one dashboard. So this is the dashboard that I use for Airflow as Scribd. It has hundreds of graphs. All the graphs are managed. The whole dashboard is managed in Python, but usually I will go to the overview panel, look at the high level metrics, and then do deep dive into each subsystems based on the kind of issues that I'm seeing. And this is what the RDS panel, expanded RDS panel, looks like in this dashboard. So having the metrics is not enough. Obviously, if anything goes wrong, we need to have a way to notify an engineer. So we also integrate with PagerDuty. This also goes back to one of the principles that I mentioned earlier, where we want to separate infrastructure from application, right? So for infrastructure incidents, we have everything go through Datadog monitors, and the Airflow team within Scribd will get paged. For application incidents, we have a integration with the Airflow operator. So we have the internal custom operator will actually emit PagerDuty event for task failures, SLA misses, or user can also define their own custom event. This will get sent to PagerDuty, but we have custom routing rules within PagerDuty so that those incidents will get routed to task owners instead of the Airflow team. So this is what a custom routing rules looks like in PagerDuty for us. So with all that, going back to the original diagram, I hope this is a lot more clear to you all. And we're pretty happy with the setup so far. And I hope some of this practice that we do here to turn out be useful for you all. And now let's talk about the migration. So the data pipeline at Scribd, it's actually really old. Scribd itself is also a really old company. We actually from the first batch of YC. So we have an in-house workflow orchestration system called DataPipe. You can think of it like Airflow, but in Ruby. The first commit dates way back to 2010. So I believe this is even older than Airflow itself. So too bad this project was never open sourced. Today we have 1,500 tasks with 1,200 of them in a single DAG. So 1,200 of those tasks are interconnected with each other. And the pipeline itself depends on some of the features that's only available in DataPipe, but it's not supported by Airflow out of the box. For the data storage, we are using all of this is running on physical servers. We're using HDFS, a little bit of S3. We're using Kafka, MySQL, Redis, Elasticsearch. All of those are managed by ourselves. For compute, we're using Hive, Impala, Spark 1, Spark 2, and Ruby. So these are the technology we use for writing the data pipeline, ETL jobs. For the new design in AWS, we want to step back and rethink about a lot of those technologies and try to simplify the design as much as possible. Obviously, we're going to use Airflow to orchestrate everything. For data storage, we are we're actually moving from HDFS to S3 with Delta Lake. So the benefit of doing that is Delta Lake actually solves a couple of problems for us. One is the eventual consistent issue with S3. And then the second problem is it makes it possible to develop both streaming and batch applications from the same data source. And then we're using Kafka, but managed by AWS. We're using RDS, and all of basically use as many managed services as possible. And for compute, we basically unify everything into Spark 3, which is through the Databricks platform. So so everything becomes a lot simpler for us, but also things became a lot faster. Now, it's not really easy. I would say that the migration process, right? So this is what the 1,200 tasks stack look like. So this is before we did the migration, and you can just looking from the DAG, it's clearly this is a big messy hairball, and it's not gonna be a fun journey to migrate everything over. So the first thing we did was to try to simulate the production run in Airflow as early as possible, right? So I think this is one thing that we did really well. The way we did that is we wrote some automation to translate the Ruby DSL into Airflow DAG. So in the old pipeline, all of the task dependencies are defined. Sorry, all the task dependencies are defined in a DSL, and each task is in the new Airflow DAG. Each task is basically a dummy operator, right? That sleeps to simulate a run, basically a remote API call and waiting for the call to finish. And then we also set the task sleep time based off the statistics we get from the in-house system. So we use the average runtime so that the full pipeline run will be as close to what will actually look like in production as possible to the Airflow scheduler. To So at the beginning, it was really we were really happy that the scheduler was able to handle this stack without any problem out of the box, until I tried to view this stack in the web UI, and this is what I got. So turns out that the DAG is so large that Airflow was not able to render this on the web UI, and basically all the requests are timing out. So what actually happened, right? So previously, to render a 1500 task DAG in Airflow, it's taking a really long time because the backend has to generate an HTML page that's almost 100 megabyte size large, and on top of that, try to render this HTML page or parse this JavaScript in the browser. It also takes really long time. Basically, the backend always time out in this case. So we look into the Airflow code base and try to optimize the hell out of this. We actually did a lot of optimizations. Some of the less intuitive ones include avoid serialize the whole ORM object. So instead of just parsing the ORM objects into the JSON encode function call, we just write manual encode functions that only serialize the fields that would be needed by the web UI to render this page. And then another thing that is to remove all the unnecessary if statements. Turns out that for a really hot loop like this, every if statement counts, and sometimes adding one extra if statement increase the runtime by 5 to 10%, which is quite surprising. And then another thing is to basically, when we generate HTML page, we write out the JSON object as a JavaScript string. So what this actually improves the web rendering performance a lot. The reason this works is because if you write it out as a JSON object, the browser will parse that JSON object using the JavaScript parser. But if you write it out as a string, it takes a lot less time for the JavaScript runtime to parse that string. And then within the JavaScript runtime, you can use JSON.parse to parse that JavaScript string and return the actual JSON object. So the JSON parser is a lot more faster, efficient, and a lot more efficient than the JavaScript parser, right? So this also speed up the web rendering time. We did a lot more optimization than just this, and you can take a look at the PR to see what other things with it to make it faster. So as an end result, we reduced the page size by more than 10x, and we improved the page load time by 5x, and we was able to finally load the DAG in Airflow Web. And this is what it looks like in Airflow. Obviously, it's not really useful if you don't zoom in. So, next I wanted to talk a little bit about how we break up the migration steps into multiple stage. The first thing that we did was set up an incremental daily sync from the HDFS data lake into S3. In order for this to work, we actually had to run some task in the old orchestration system and some task in Airflow in Databricks. So we decided to use Airflow as the orchestrator to orchestrate the whole daily sync process. So basically, we have to teach Airflow to we have to write a custom Airflow operator to run this task in the old in-house system. And in order to use Airflow DAG as the single source of truth for the task dependency and definition, we also wrote a mini Python parser in Ruby so that the in-house system can actually parse the Airflow DAG and understand the task dependencies, and as well as the task config. So after we have this daily sync, incremental daily sync working, the data that we produce in HDFS, it will be available in AWS on daily basis. And then we can move our users to the Databricks notebooks for any kind of read-only interactive queries. So these users, they used to run these queries in Hill, which is a lot slower, and there's no easy way to share the queries with other team members to collaborate on stuff. But just having this ad hoc query capabilities in Databricks notebooks open up a lot of new ideas and definitely made the whole team a lot more productive. And then before we start the actual migration, we also want to trim the dependency DAG for a pipeline that's more than 10 years old. There's a lot of legacy crap in the task dependency graph. So we want to. This is actually a really good opportunity for us to really look into that and delete things that's not needed anymore. And once that's done, the next phase is to move the output layer of the pipeline into Airflow and into the cloud. The reason that we want to separate this part out is because it actually delivers business values to the rest of engineering team. One good example is that this layer of the pipeline is responsible for exporting the offline batch output into some of the online data stores like MySQL or Elasticsearch. By doing this, we can actually speed up drastically the whole exporting process a lot, and so that and those external services will have a much more stable export experience, as well as a much more a lot faster data, in the online data store. So this is the phase that we are at right now. And then once the output phase has been all migrated, we will then work on the remaining of the pipeline, which we already have the tools in-house to automate a lot of the task generations. We basically just have to change the simulation run script to generate the actual task that will be running in Airflow, and then we can move those tasks piece by piece into Airflow and into the cloud. So that's all I want to talk about. A little bit about myself. I'm QP. I'm an engineer at Scribd's core platform team. I'm a new Airflow committer as of this week. And I'm also a maintainer of contributor of many other open source projects. You can find me at the Airflow Slack channel, Airflow mailing list, and also have my contact in my personal website. And a closing thought, this whole migration effort, it's truly a team effort between different engineering teams at Scribd. It's driven by the platform engineering team, which consists of core platform and data engineering team. Scribd as a company fully embraced the open source community. Since the beginning of this project, we have contributed 41 patches to upstream Airflow, and we expect many more to come. And if you're interested in working on open source projects, solving engineering problems and helping people read, we actually have quite a bit of openings. So feel free to check it out. That's it. Thanks, everyone.
Thank you so much, QP. Give us a second. Okay. Thank you so much, QP, for sharing that presentation with us. We have some time for questions, so we'll start addressing them. The first question that we have from Shabarish. He asks, why not use EFS or persistent volumes for DAGs?
That's a really good question. We had a really detailed explanation on the technical choice about this. So S3 versus EFS in our blog post. So I definitely recommend you to check it out. In brief summary, the reason that we prefer S3 over EFS is S3 is a lot easier to manage from our end. Everything can be accessed through RESTful APIs, and it's a lot more available, highly available. It basically it's a lot easier to operate for our case, and we don't have to mount EFS mount on different containers or different Kubernetes pod. As long as you can talk HTTP, then you can access that. So it's a lot easier to set up and operate.
Great. Okay. The next question, actually from the same user, but let me try to adjust the syntax to make see. So the question says, how are DAGs from S3 syncing into Airflow web server and the scheduler ECS nodes? Yeah. How are
So
the DAGs from S3 syncing to Airflow web server and scheduler?
that's also a question that have a detailed answer in the blog post. But to give a quick overview on that is we run this vaccine daemon as a sidecar container for both web and the scheduler, and they share the same transient volume mount within ECS. And for the Kubernetes executor part, we actually just use the git sync container feature and just run this daxing daemon once at the beginning of the task, which basically acts like a git clone, and then we just run the DAG from there.
Okay. Next question that we have from Soliman is, how do you deal with the incremental amount of Airflow logs? How does it affect the UI?
So the logs doesn't really affect the UI performance for us. Because the logs are actually stored in the S3, right? So what actually gets stored in the Airflow meta store, it's just the pointer to the S3 URL. So it has minimal impact in terms of the performance.